Great. Thank you for sticking around to the end. We'll be talking about Nixon Hydra in particular from JBST, NearCam imaging. And I want to point out here that this work was primarily done in conjunction with a high school student. Derek just finished his first year at NYU. So in that intervening time, I've made some updates to the analysis, made some more plots and worked on the interpretation, but a lot of what I'm presenting is based on his initial analysis. All right, so a little bit of motivation, right? The previous talks we've heard about origins, dynamical evolution, physical properties of the minor satellites. But I want to talk a little bit more about what their compositions can tell us potentially about the progenitor object or objects that form the Pluto system. And we have so many beautiful JBST spectra now from many different programs. So how do these minor satellites, their compositions, compare to the larger TNO population? So overview of the flyby, some of the compositional information from New Horizons. We got beautiful images of Nixon Hydra, and as well as near-infrared spectra of both of these objects, showing very strong water ice features, including the 1.65 micron crystalline water ice feature on these very small objects. There's also a 2.2 micron feature typically attributed to ammoniated species that's present that certainly deserves a closer look. And the colors are roughly solar. Nix appears to be pretty close to the solar color. There's a little star in the center of this plot, which marks the color of the sun. And there's a little bit of a red splotch on Nix that extends that a little further. But for the most part, they're neutral-ish in color. So you may be surprised to find out that JBST can do a pretty good job of observing these objects. We obtained three separate epochs of images, or epoch might be a little bit generous. They're over the course of one Charon orbital period. So we did that in October of 2022. There were 4 different filter sets used. So there's a short wave channel and a long wave channel in NearCam that observed the same field of view at the same time. Each individual image was 12 seconds in duration, and there were 8 images basically taken together, averaged in each of 2 dithers. However, there's an incorrect dither setup. So in one case, for the second dither, the Pluto system was in a chip gap or off of the subarray. So we essentially got 1 dither in each of these dates. And now you've been sitting through this conference for 4.5 days of mind-blending science. If you feel like you have a smoothie between your ears, the one thing I want you to take away from this is that each of these images that I'm going to show is 90 seconds in duration. So here's the shortest wavelength filter on NearCam, and I've circled the positions of Pluto, Charon, and the minor satellites based on Horizon's values. And in those 90 seconds, approximately 90 seconds, we are getting signal noise ratios between 5 and 10 on Nixon Hydra. And if I go through here, you can watch them orbit. All right, I'll go back to the beginning. Whoop. All right, so we wanted to get more or less full rotational coverage on Pluto and Charon, and these images were made specifically to observe Pluto and Charon, yet Pluto's still kind of saturated. But in this case, Nix and Hydra end up as bonus science. They weren't expected to be there and observable. However, we don't get anything from Styx and Kerberos, unfortunately. They are a little too faint to be detected in any of the images, and we also don't get Nix and Hydra in any of the long wavelength images, right? As we've seen in a lot of these spectra, once you go beyond 2.5 microns, the flux just drops. So, but we were able to get Nix and Hydra in all of the 4 shortwave filters. So we did aperture photometry, applied aperture correction factors, honing in on each of the individual objects, and due to shorter rotation periods, and things like that, we did a weighted average of all 3 nights for Nix and Hydra, and basically did a, I don't know if you can call it really a full average of the object. I'm not really sure which phases we got, but it helps increase the signal noise a little bit further. So first I want to show a solar comparison. As I said, they're roughly neutral in color. So the 4 filters that we observed in were the 4 shortest near cam filters. We see roughly follows the solar trend with a little bit of reddening at the shortest wavelengths. So a comparison to Charon as well is presented. We did some synthetic photometry of a PSG solar spectrum to get reflectances, and normalized everything to the central wavelength of the F115W filter. So you can see Nix and Hydra are very similar in their colors at these wavelengths. And they differ a little bit from Charon, which is redder than the minor satellites. I'll talk about that a little next few minutes. Here's a direct comparison to the Charon spectrum from Sylvia's paper. Luckily, the Charon, I'm saying Charon and Charon, I apologize. The Charon photometry matches pretty well with the spectrum, which is fantastic. I note that the Nix point at 1.4 microns is a little lower than it is for the other objects, but I think this is what happens when you average 3 points together. There's no reason to believe that the Nix photometry there should be lower than for the other objects, given the comparison of these spectra from Jason Cook's paper. Right, Nix is not the most water-rich object of the minor satellites. So I think that is a bit of a spurious point, but I mean, can I throw out 1 of 3 points? I think that's a philosophical question. Comparing to colors of the disco sample, we have all of the familiar now bowls and double dips and cliffs all occupying a space up here at the top of the plot, with Nix, Hydra, and Charon in distinct locations in this color space, this particular color space given the filters that are available to us. Here's a direct comparison to the spectra themselves for bowls, showing the photometry. Everything's normalized again to the F115W filter central wavelength. And I'll go through. Here's the double dip. Right, we're not seeing complete, real complete agreement. Looks even worse for the cliffs, but we get some, better agreement with, Haumea family members, right? Water-rich objects, as we saw, from New Horizons for Nix and Hydra, with that turnoff at shorter wavelengths. So the Haumea family is not even neutral; it's like blue slopes at the shortest wavelengths. So in this sense, Nix and Hydra are kind of red Haumea family members, neutral in color compared to the sun, but red compared to the Haumea family members, with still a similar surface composition. So there's been a lot of talk throughout the week about material transfer within the system. Escaped methane from Pluto's atmosphere is thought to accumulate and make its way to the pole of Charon and produce the red surface there. But this material doesn't make it even all the way out to Nix. A lot of it is scooped up by Charon, and the little bit that's picked up by the smaller cross section of Nix is probably not enough to contribute to any significant reddening of the surface. You also have the rotation pole is changing over time, so you don't get necessarily long-term cold traps like you do on Charon, where that material can be retained and processed. You also have dust ejected from micrometeorite impacts, leaving the minor satellites and making its way to the surface of Charon. So in this sense, Charon acts as a kind of a crossroads or even a vacuum cleaner in the Pluto system. It's collecting material from Pluto, it's collecting material from the minor satellites, but it seems unlikely that you're getting anything from those objects onto the minor satellites themselves. right? You're not getting the methane that's escaping Pluto's atmosphere onto the minor satellites. And do you have enough velocity to eject material from, for instance, Charon onto the minor sats? So in that sense, maybe the minor satellites represent the surface compositions of the progenitor body. Sounds like that would mostly come from the proto-Charon based on the kiss and capture theory, right? So we're maybe seeing the primordial composition of the proto-Charon. I don't find this to be a particularly profound statement. Bill even mentioned it offhandedly as a comment for someone else's talk, right? It's almost obvious, right, that this might be the case. But maybe there's something else going on here. If these objects do represent the original material of the proto-Charon, and you now have that material being redeposited onto Charon over time with up to centimeters thick amounts of dust accumulating over the age of the solar system. Right, we might be seeing Charon today as it was then. You look at the size of Charon compared to other similarly sized objects, Quaoar, Sedna, Gong. Charon is actually larger than Quaoar, larger than Sedna, similar size to Gong. And based on JBST spectra from Josh Emery's paper, we're seeing organic species on all of these objects, right? Short chain hydrocarbons. We're seeing methane on Quaoar, which is smaller than Charon. So why are these missing on Charon? Is it because we now have Charon reaccumulating its initial material from the minor satellites? I think it's something interesting to consider. So summary of these this bonus science, right? We see slightly redder than neutral colors of Nixon Hydra are confirmed with JBST. On average, their colors are a little less red than Charon, probably because of that red pole. You have mostly, in this idea, you have mostly Nixon Hydra dust plus this imprinted red pole from the capture of methane and capture and processing of methane. Nixon Hydra are basically indistinguishable at short wavelengths, and that tends to agree also with the similar albedos for the objects and also compared to Charon. They occupy unique space in color space. They don't match any of the other spectral types observed by JBST. There's some difference in compared to all of those other types, including to the Haumea family. In general, it looks like Nixon Hydra surfaces may be unaltered material from the initial impactor that is being redeposited onto Charon. Of course, it'd be great to get more data. Who doesn't want more data? So there's a possibility that maybe we could look into spectroscopic observations with JWST, get the full 1 to 5 micron spectrum, look more into the ammoniated materials at 2.2 microns, look at, is there CO2 present on these objects as well? We see it everywhere else, so my money is on yes. We need to obtain these spectra to determine that. And just in general, continue to compare to Charon, which they seem to be interacting with in a significant way. So that is my rather fast talk. Happy to take questions.
Cool. A few thoughts spring to mind. One is that it would be really nice to compare it to Charon without the red pole. You can't do that with the JWST data, but that is getting into the MVIC wavelengths where they differ. So it might still be possible to do that. And then the other thought is, if I remember correctly from Simon's models, the dust wasn't uniformly distributed in longitude when it arrives at Charon. So it was, okay. Yeah. So it was on Pluto that was non-uniform. Okay, my bad.
Yeah, for really fast particles, I think from your paper, really fast particles coat the surface of Charon more or less evenly longitudinally.
Yeah, because the high inclination ones uniformly get swept up, whereas it's only the low inclination ones that make it down Pluto.
Um, Two questions, and they're tied by the question of what do you get from JWST that we didn't get from New Horizons. So you lose the flux as you go longer. Um, how far out to what wavelengths do you think you can detect Nixon Hydra if you were to do it with spectra? The first part.
I believe that they can be observed with the low resolution mode, the R of 100, probably in a few hours, uh, to get decent signal noise all the way through the spectrum.
All the way through.
1 to 5. Yep.
Okay. Well. Okay. Okay. Well then. So the second one is a little more mealy-mouthed, which is taking Simon's pole positions and saying, are we looking at it at different places on it than we saw with New Horizons? But um, the first answer trumps.
So for your second question, one thing I forgot to mention here, it was in my original set of summary points, and was related to the question I asked Simon. We're finding from this photometry that Nix or Hydra has higher flux than Nix, which is strange given that. So maybe since the time of the flyby, you've seen a change in the pole. So you're suggesting that?
Yeah, it was still pretty pull on during flyby. I think it's just become slightly more so. The fact that we saw any light curve at all from approach was really just the fact that it has such a complex shape. If it were just like round, you would have seen no light curve on approach. But it's just this funky shape.
Okay, so it's not weird that Hydra has higher flux than Nix in these images.
Yeah, and that's what we've historically seen with HST as well.
Okay.
Thank you. Bryan, wonderful talk, fascinating work. I'm confused, and maybe you can help me between I don't understand the statement Nix and Hydra do not match any of the TNOs. So any of what we think are unaltered original bodies out there, and the statement that Nix and Hydra appear to be unaltered. I would have logically assumed that they were altered by the collisional process, and that's why you're not getting the match between them and the TNO population you've surveyed.
Yeah, so I think
Can you help me with the logic there?
those 2 points are not necessarily related. One is pointing out that they are distinct from all of the other TNOs that have been observed so far. Right? Obviously, Pluto. Every day this week we've seen that Pluto and Charon are distinct objects as well.
Right.
So we're seeing that none of them match the general broad spectral types across the larger region. So that's the first point. The second point is that based on these ideas of material transfer within the system, there should be an expectation that you're not having Pluto and Charon altering the surfaces of the minor satellites, and that instead they represent the information on the original proto-Charon.
Okay, I think there's an assumption there that the material that goes into the moons is unprocessed by the formation of the moons.
Okay, I guess we're arguing then about the timeline of unaltered, right? What does unaltered mean?
I don't mean to argue.
Yeah.
I'm trying to understand better.
No,
We can
yeah.
talk about this offline if you like. Just trying to understand the hypothesis and the logic.
Yeah, I guess in that sense I meant it's not. So while it may have been altered by the impact itself, it has not been altered in the intervening time since then.
I see. And it's certainly possible that the Kuiper belt is quite collisional, right? So a lot of these bodies could be collisionally processed, and that gets into the survey and the spectral results. But yeah, thank you.
Yeah, let me offer a comment. A few centimeters of Hydra or Nix pollution onto the surface of Charon, it's not an inactive body. You have regolith formation processes over billions of years. You're not.
Oh, yeah.
You're going to mix it into the.
I'll say that number is entirely based on sort of a model for how much how many impacts you have to have onto Nix and Hydra, which I'm not sure if that's still accurate. What I did back in 2015 based on the cratering, because that was before we had any of the images.